So I'd like to talk about an interesting circuit configuration, in this particular case for an nFET circuit. Now, the circuit that you see over here has a very interesting set of properties. Now, it's an nFET device. We would actually expect a couple of things. One, we have a voltage here. We have another terminal. The other side of that terminal, the source drain junction, is half a volt, and the gate is at 0.8. The substrate is at ground because implicitly that's what you would always get unless it's, if it's not specified, and that's what you'd expect in any sort of n-well process, as this is how it's going, what you would end up seeing. Okay, great. So now you look at the circuit and your first couple things are, well, I should just be able to plot and analyze this. No problem. Until you ask the first question. Well, is this voltage V a source or a drain? And the answer is it kind of depends where you are. Now we're going to take a look at that voltage V sweeping between 0 and 1 volt. And what's going to happen is this is going to definitely change. So when the voltage is greater than half a volt, well, we know that then the current's going to flow from that drain to the source. For an nFET, you end up flowing, carriers go from drain to source, at least in terms of the electron current. Now the carrier is actually source to drain, but remember there's a sign inversion there. Okay, so I can at least look at that range, and if I do that, it looks like a pretty standard FET. And I can look at, for example, the subthreshold operation. Let's just kind of look at that part of it for the moment. And I would simply write down the whole curve, which with everything involved. So this is subthreshold, allowing for the ohmic and saturated region in the subthreshold regime. And notice I'm mostly just plugging in variables. And when I want to look at the saturation case, it's sort of when this term here gets to be negligible compared to 1, which typically happen about at when V is basically at 0.6 or greater. And so that makes sense. And in fact, if you plot that part of the curve for these particular parameters, what you're going to notice at half a volt and 0.8 volts, when, starting with a threshold voltage of 0.25, sigma 0.0025, threshold current 100 nano, is you get something right at about 1 nanoamp-ish all the way through here. From 0.5 to 0.6, you see this sort of classic curve going from subthreshold, going from ohmic to saturation. It's 100 millivolts, and it really does very quickly get to a convergence point. And what you then see after that is that it's relatively flat, but if you looked at it and zoomed in closely, there's a slight slope, and that's due to sigma. Okay, so that would make a lot of sense for this device. And so you could kind of look at, okay, here's the slope and how you would create it. Now what happens when the voltage is less than a half? Well, we have a very interesting circuit at that point, because now if it's less than a half, the current's actually going to flow from 0.5 down. So the current will become negative. So we'll have a change in sign, although of course when we're plotting the log of something, you can only plot magnitude, so the sign will change. And this is now the source voltage. Well, now I'm going to be talking about what happens when I take the source voltage and bring it down in potential. Well, as I decrease source voltage, I often increase current. And so in this case, we're not going to be too worried about the drain effects, because the source effects are going to be much, much stronger. And that's self-consistent when you actually look at the data. And what you see here is that it's going to be the source is sitting that minus V right here. Right? And so when and then you don't really have to worry about the sigma part, so basically it just turns out to be the V. You're like, okay, what does that look like? Well, that's going to be an exponential function. Now at first it's going to have some interesting issues at the low currents, because again it's still got to get through all of this, as we had here. It's still got all of this in play. This, if you look at closely, this equation is still basically valid, it's just we're simplifying it in a reasonable place. And that'll work really well until you get a high enough current where you cross the threshold current. And at that point, it's now going to be above threshold. And at that point, an expression that basically hits the above threshold behavior is a sort of quadratic function. Obviously minus V squared in here. You've got K over 2 kappa, and you work with this. Those who don't remember, there's sort of this relationship between threshold current and K. to kind of go back and forth. If this is the case, you get about 112 microamps out of that per volt squared. And from there, you can say, okay, what kind of curves do I get? And I get this very rapidly increasing curve on the other side. So yes, this is actually a very asymmetric curve. A couple interesting things is that this will actually have 1 over UT slope, UT being the thermal voltage. And so you'll definitely see that there's a crossover point here. And that really occurs like basically when I'm right at threshold, right? And I can look at that condition for threshold, which is where kappa VG minus VT0 minus VS is 0, and calculate for that, and it's really at about 0.385. Really interesting that you can kind of piece that apart. Notice that is not a threshold voltage per se, but it's related to all of these terms. Remember, fundamentally, threshold current is the fundamental term. But otherwise, we can actually solve this. But I think most times people are not very familiar or comfortable with the fact that, in fact, all of these different things are in play. And with what is a very simple sweep, I can actually see all sorts of physics out of one, and all sorts of very interesting computation out of one single device.